Okay, so second half of the video, or second half of the lesson. So we're going to look a little bit at boxplot. So boxplot is really just another way of graphing numerical data. So here's some disadvantages of a boxplot. One is that it does not retain the individual values. So just like with a histogram, we're not able to see what actual individual values in our data set are. But a boxplot is probably even more vague than a histogram. The only individual values that I for sure see are like the minimum, the maximum, and any outliers that we have. So that is one disadvantage. Second is that we cannot see gaps. If there are big gaps in the middle of the data, obviously we could see if there are gaps between like outliers, but if there are gaps in the middle of the data, we cannot see that. And we also can't tell anything about modes. We can't see like peaks, those peaks that we see on a histogram or a dot plot or a stem plot. We cannot see that in a box plot. So we cannot tell whether the data is uniform or unimodal or bimodal or multimodal or whatever. We can, however, tell things about the symmetry of the graphs. So symmetric box plot is basically going to be about the same distance from the median to the maximum as from the median to the minimum. So that kind of distance from the median to either side of the data should be about the same on a symmetric box plot. So I have on here a couple of symmetric box plots. There's 3 of them. The box plots look symmetric, and then I'm just kind of showing you the histogram for each one below the box plot, and you can kind of see like those box plots look almost identical, but in terms of modes, they looked very different. So we cannot tell anything about modes, but we can tell things about symmetry. A approximately symmetric box plot. So here's one where it's not perfectly symmetric, and even within the inner quartile area, it looks off center or skewed. But remember, for symmetry, we're comparing the median to either side. So this would be something we'd consider approximately symmetric or roughly symmetric. And then a skewed box plot is going to have a longer distance from median to max or median to min. Wherever the longer distance is or the longer tail is the direction of the skew. So this one on this example would be skewed to the right or to the higher numbers. So let's move on and talk about measures of center and spread. So dealing with we've already talked about a couple different measures of center. We've talked about mode or peak. We've talked about median, but now we're going to look at one more, which is mean. And then we've talked about a couple measures of spread. We've just dealt with range, or just listing the minimum and the maximum. And then we've talked about IQR, which is another measure of spread, but we're going to look at one more. So measures of center are mean, median, and mode. Okay, so let's look at 2 groups of fake test scores. So here's group A and here's group B. If I'm looking at those numbers, you can kind of see that they do look pretty different if I'm just looking at the values. However, if I were to just tell you the measures of center, they actually have the exact same mean, median, and mode. So if I'm just telling you, and center is usually telling us what's typical or what's average about our data. So if I were to just tell you, hey, for these 2 groups of test scores, they're about the same. They have the same mean, the same median, the same mode. Then you might think, oh, these 2 classes are doing pretty equal. But when you actually look at the numbers, you can see that that's not true. There's differences in those 2 groups of data, and it has nothing to do with the center or the average or what's typical. It has to do with the spread. So measures of spread are a really important part. We also call this variability. It's an important part of statistics because we cannot just look at the center and what's average and what's typical. We have to look at how spread out the data is. That's going to tell us a lot about what's going on. So our measures of spread are range, IQR, interquartile range, and standard deviation. Okay, so let's talk a little bit about standard deviation because that is not something that we've dealt with before. You hopefully know what the mean is. The mean of a list of data is to add them all up and divide by however many there are. But standard deviation, this is our equation for standard deviation. This is not typically something that we do by hand. And I'll kind of show you in our next lesson on the calculator how we can get it really quickly. But standard deviation is kind of the average or typical distance from the mean for each value in our list of data. So our formula, it looks real complicated. It's not as bad as it looks, but basically we take each number as the x and subtract the mean. So we're figuring out how far that value is from the mean. Then we square that distance basically to make it positive. And then we divide by n minus 1. There's a reason we divide by n minus 1 and not n, but that's a long story that I'm not going to get into. That's to kind of find the average. And then I take the square root of that to kind of undo the squaring that I did earlier. So that is our basic standard deviation formula. If we left it as the number inside the square root without square rooting it, we would have standard deviation squared, which is called the variance, which is another measure of spread that we'll deal with more later in the year. But variance is a thing. It's just standard deviation squared. And it's another measure of spread that we deal with sometimes. So let's practice. And I'm going to try to write with my trackpad here. So let's practice with this smaller set of data to find the standard deviation. So the first thing I'm going to do is find each value's distance from the mean. So the mean is, I probably should have done that first, huh? So we have to find the total number of values we have, that's n, which is 5, and then the average of those 5 numbers, which is 7. So I just added all the numbers up and then divided by 5, and we got 7. So we needed to know that first. So now that we know what the average is, we are going to find the distance of each value from the mean. So 2 minus 5, 5 minus 7, etc. So I'm going to find each value's distance from the mean. So then once I've found each value's distance from the mean, the next job is to square those distances. So then I'm going to go through and do this part of the math right now. So 2 minus 7 is negative 5, and negative 5 squared is 25. So I'm going to go through that. 5 minus 7 is negative 2. Negative 2 squared is 4. So make sure you keep it positive because we're squaring it. So now I have all of the distances from the mean and then squared. My next step in that formula was this little symbol right here, which basically just means add them together. So my next step is to add those 5 things together. So those numbers added together is 80. So that is giving me the top fraction part of my formula. So now I have 80 on the top inside the square root divided by n minus 1. So we had 5 numbers in our data set. 5 minus 1 is 4. Okay, so then 80 divided by 4 is 20. So 20 would be the variance, but then the standard deviation would be square root of 20, which we are just going to go ahead and put as a decimal. In statistics, we kind of like the concrete numbers as opposed to leaving them as radicals, which is technically more exact, but in statistics, we like concrete. So our standard deviation is 4.47, which is the average distance from the mean. So for these 5 values, the average distance from the mean of 7 is 4.47. So that is how we do the standard deviation by hand. And next class, I will go ahead and show you how to do that. Hold on. To erase all my writings. Okay, so now we are have standard deviation. So we're going to go back to those values and look at what the standard deviation is. Again, I will show you how to do this next time on the calculator. Oops. Okay, so the standard deviation for group A is 4.77. And then the standard deviation of test grades for group B is 18. Oops, that was a weird 8, but it's 18.22. It's really hard to write with this, with the trackpad. So we can definitely see that's 18. I was trying to fix it, but 18.22 versus 4.77. And we can kind of see that just by the fact that the datas in group A are more spread out. But remember too that data values in group B are more spread out. The standard deviation is not necessarily how far apart the values are from each other. It's about how far apart the values are from the mean on average. So let's talk a little bit about comparing the measures of center and comparing the measures of spread. So mean versus median and what is considered average. So let's say, this is my silly example for today, Ken and Barbie go house shopping. So they're gonna go buy a new dollhouse. Here are some prices for dollhouses in one neighborhood. Right, so these are some fancy dollhouses. Those are the prices. Here's a dot plot of those 7 prices. And here are 2 more values that they find for houses in their neighborhood. So for the original 7, the mean was $507.14. The median was $500. But then they went and they found 2 more houses that are like exorbitantly priced, ridiculousness. So here's my new dot plot, right? Here are my original 7 values, and now here's the 8,000 and the 10,000. My new median is $500. So my median is still $500, but my new mean is now $2,394. So when you were asking Ken and Barbie, or when you're finding out for this neighborhood, what is the typical or average price for this neighborhood, if I list this value, no one's going to go to that neighborhood who has like a smaller budget. This is ridiculous. This is a high price. It makes you think that most of the houses are in the thousands of dollars, when really for most of the houses, what's typical is closer to this 500. So the whole point of that is to say that if we have a distribution that is highly skewed in one direction or has outliers on one side, especially major outliers, the median is a better measure of center than the mean. Okay. So the thing is that the mean and the median and mode are all affected differently by skewness. So if a distribution is what we call normal, which means it's symmetric and unimodal, the mean, median, and mode are all going to be in pretty much the same spot right in the middle. But if we have a distribution that is skewed to the left or skewed to the lower numbers, that mean is going to be pulled to the lower numbers pretty significantly. Median might move a little bit, just kind of depending on the numbers. Mode's pretty much not going to move at all. And the same thing happens the other way. If we're skewed to the right, the mean, or to the higher numbers, the mean is going to be pulled to the higher numbers pretty significantly. Median might move a little bit, but mode's not going to move at all. So when we talk about measures of center that are appropriate for different distributions, we have to think about how they are affected by that skew or by outliers. Okay. Just as a quick example, in the 1980s, the average yearly salary for students who had majored in cultural geography at UNC was over $100,000. That was the average. So then everyone's like, ooh, maybe I should major in cultural geography at UNC because apparently I can make a lot of money. But let's look at a quick graph. Just to compare, the average salary for that major at most other colleges was only around $20,000. So something fancy is happening at UNC. Okay. So here is our dot plot, or actually histogram. Here is the majority of our data in terms of salary for people with that major. And here is Michael Jordan. So that was his major, and that was his salary. It had nothing to do with his major. It had to do with who he was. And that mean, or I'm sorry, that one value, because it was so high, pulled up that mean pretty significantly and made it seem a lot higher than it really was. So the median would have been a much better measure of average for that group. Same thing with standard deviation versus range. So, same thing, Ken and Barbie, there's our original 7 prices. There's our dot plot. The standard deviation of those 7 prices is $78.68, which basically means that typically house prices in this neighborhood differ from the mean house price by about $78.68. That's the typical distance from the mean. The IQR for that set of data is $100. So somewhat similar in terms of measure of spread. It's telling us how spread out the values are. There's our 2 exorbitant house prices. There's our new dot plot. My new IQR is 150, so IQR went up a little bit. And my new standard deviation is $3,778.84. So, for a distribution that is skewed or has outliers, the IQR is a better measure of spread than the standard deviation, or the range for that matter. Standard deviation and range are both going to be very affected by those really, really big skews or really big outliers. The IQR is giving us a better idea of what's typical in terms of how spread out the values in that place are. Most of the house prices for Ken and Barbie in that one neighborhood were fairly close together, within $100 or $150 of each other. It's just those two that were crazy big. So when we talk about how spread out values are, if it's skewed or has really big outliers, the IQR, interquartile range, is going to be a better measure of spread, because spread or standard deviation and range are going to be very highly affected by outliers and skew. So here's our quick little summary of what we just talked about at the end there, just to have it all in one place. If your distribution is roughly symmetric, it doesn't matter what measure of center you use or what measure of spread you use, they should all be fairly similar to each other. But if your distribution is skewed or has major outliers, median is our measure of center that is preferred, and then IQR is the measure of spread that is preferred. So that is the end of today's lesson, finally.